Okay, team, let's go. So I have some very nice things to show you today, as always, in Matrixology. Beautiful things. We're going to do a little bit of, we're going to play around with this innocuous little matrix here. 1, 1, 1, 0. Nothing in it, right? But this is full of gold. Beautiful things, beautiful things. So Fibonacci here. We're going to have to talk about change of basis. It's a very elementary thing. I want you to just understand this, what we're doing when we do diagonalization. And I'll tell you what this is about in general, how we can do it with linear algebra. Then we're going to talk about real symmetric matrices, providing I don't monologue too much, and how they and what happens to them when you diagonalize them. So real symmetric matrices have incredible properties, which I'm sure you're thrilled about. Yeah. These are pretty crazy. And we'll get to this as well, which is part of this, the spectral theorem. Very weird thing. All right, so first of all, it's springtime, right? No? Yeah? So team, let's go. This is very important. You should watch this. So last year we had a baby robin fall out of a tree, and we couldn't get it back up in the tree, so we had to look after it. And I had no idea that robins are just such beautiful little birds. So this little creature is pretty plump, and we think its name is Tsubasa, which is my eldest daughter's coining, which means wings, a wing in Japanese, I think. So we're going to go for a little walk. We just hang out with us all the time. It's a very dopey little thing. And the parents would come and feed it every day, right? So the parents don't leave. They feed these things for about 3 or 4 months. But we had to keep it inside because of all the cats. And its basic dopiness. And there you go, bird cam. It was really the sweetest little bird. It was great. We'd just sit there and chirp with you all day. And the parents would get upset, and so we'd bring it in every night. Anyway, eventually flew away and lived, which was pretty great. Lots of strawberries went into this bird, but we think it came back, like yesterday. And then, of course, it snowed this morning. So all the robins are like, what are you doing? So I think that, right? They're putting little backpacks on, migrating birds and all sorts of madness, yeah? Oh, there's the GoPro on the eagles. Yeah, the eagle, yeah. Robin, this one would not be a good GoPro. Anyway, pretty great. So I threw up, that should say level 9. I threw up, okay, this is important, I threw up level 9. It's Qbert, which is a pretty exotic game. If you've watched Wreck-It Ralph, Qbert is homeless in Wreck-It Ralph, for good reason.
So right there, both of those are due next week.
Yeah, I'll fix that little.
Okay. So which one actually due?
So it should be due.
Okay.
So this is what happens when your brain doesn't work. 21. It should say it in the thing properly. Okay, great. Take your time. Okay, it'll be fixed. Okay, so Qbert is in there. That'll take a little while to upload, apparently. And that's due a week from Tuesday, when you have your 3rd exam. So there's plenty of time. So there's things you can do in there already, right? So you can work on some of this diagonalization stuff. That's sitting in that one, so I would get started on it. What else have we got? There's a talk tomorrow. I'm just going to advertise this. So I'm a director of the Complex Systems Center here. Simon Dedeo is coming, and it'd be very interesting. So he's a physicist who's running around working on interesting things. Information theory and the civilizing process in London's Old Bailey. So he's taken all the text from the Old Bailey and all the stuff with criminals and so on. Some of them ended up in Australia. About a quarter of them ended up in the US, actually. So always good to remember that. Then there was that War of Independence thing, and then they said, let's send them somewhere else. So anyway, very interesting analysis. And he does lots of cool things. So he's at Indiana, part of the Santa Fe Institute as well. So you should check that out. Oh, and there's food. There's food. We're not silly. Okay. All right. So I'm going to close that. And we only have 5 more lectures, including this one. All right. Right. Okay. Okay, team. Brains on. Let's do it. Okay, so I'm just going to give you a little touch of this. So my final exam for linear algebra thousands of years ago, I was incredibly sick again, I guess that time, so I ended up having to do it in the professor's office. Remember that. But it was I think it was kind of one question, and it was this question. It was just solve the Fibonacci problem completely. Because it has everything in it. There's diagonalization, you've got to find eigenvalues and eigenvectors, and yeah. All right, so I'm going to give you a sketch for this thing. The Fibonacci numbers. Okay. So I mentioned this ages ago when I introduced eigenvalues and eigenvectors as an example. And the plan is, right, so we have this sequence, very famous. Right, so if you're writing a thriller, you always stick in the Fibonacci thing because it just has that level of mystery about it. The Da Vinci Code sitting in there. It's like, oh, really? Anyway, it just elevates it. So, and I guess there are, this has been around for thousands of years. You can find it in ancient Indian literature. And Fibonacci is about 1200, something like that. In Italy, decided this was a good model for rabbit breeding. Okay. So the idea is not the best. So it's the number of rabbits at month end. And so it's sort of number of rabbit pairs, I guess, something like that. And so the idea is Fn is equal to Fn minus 1 plus Fn minus 2. So these all beget another set of rabbits. You already have the ones that exist. These ones aren't breeding until the next month. That's kind of the idea. But it leads to, and we have to see this, leads to exponential takeoff, which is, a real feature of ecological systems where there's nothing eating you or anything like that. Okay. All right, so we've got this, and we've played around with this before. So the idea was, some monks, there's lots of monks will be involved today. They say, well, what if you do this? Put Fn, I'm going to write as, this is a vector, as Fn plus 1 with Fn here. Just stack two Fibonacci numbers like this. Make a little vector out of them. And that should be, let me make this Fn and Fn minus 1. And then we can say, all right, well, here's the map, if you like, that takes, this is going to be our A, that takes us from Fn minus 1 to Fn. And so here we'd have Fn minus 1, Fn minus 2, and this is equal to, this is our Fn minus 1. All right, so this little vector, two consecutive Fibonacci numbers, is this little square matrix times the previous two, well, sliding across. People get a little carried away with Fibonacci numbers appearing in nature, the petals of flowers, the number of them is always Fibonacci. It's not quite true. But if you do look at things like pine cones and so on and count the number of spirals each way, so you count them one way, you count them the other way, there'll be consecutive pairs of the Fibonacci system, which is strange. And there's a beautiful kind of explanation for that. Pine cones, things like pineapples, yeah. So next time you've got a pine cone in front of you, count the spirals one way and then the other way. And you'll get things like 8 and 13, 13 and 21. Beautiful work by Yves Couder, who's a French physicist that looked at this. Okay, all right. Very beguiling, you think God's involved in magic, so, okay, all right, so let's see. So we've got this little matrix. So we know now that if we wanted to figure out what the nth Fibonacci number is, we'd have to raise this to the power of n, right? So the idea is, let's write it like this. So this would be 1110 squared times, it'll be Fn minus 2, and we keep going down, and we'd end up with 1110 to the power of n f0. Should I call it f0? n minus 1 times f1. And so in here is f1 and f0, which is equal to 1, 1. That's our initial state. Right, so we apply this, so we need to figure out the nth power of this thing. All right, so diagonalization. We use diagonalization, right, to find, and then we're done. It would be a horrible business to do this without diagonalization. I mean, you just couldn't, you can't do it. You can tell a computer to do it, but you wouldn't get any sense out of it. All right, okay. Okay, so that's good. So let's diagonalize it. So it's a tiny, so it's just got some ones and a zero. Strange thing. All right, so step one, find E values. And we do this by saying A minus lambda I. We set that to 0, the determinant. Right, determinant, 2 straight lines. So write that down. Put A in and put the lambdas in and write it down. This one? Yeah, so this is this whole vector. It's a little f. Yeah, so little f is the vectors, big, I mean, it's unfortunate notation, but the big f's are the numbers. Usually the capital letters are matrices. And, yeah, okay. So we got this. Right, I'm going to put everything in, 1, 1, 1, 0, minus, it'll be lambda, 1, 0, 0, 1. I don't have to write all this out, but I'm going to do it. Okay, so it's a determinant of, and we're really subtracting, you're always subtracting the lambdas from the diagonal. So there's a minus lambda here, a 1 here, a 1 here. Determinant of a 2 by 2. Right, so if it was a 3 by 3, we'd need to use this cofactor thing, and I know you've all watched that video. But it's a 2 by 2, and we know the formula for that. This goes back to our parallelogram calculation. So I'm writing here, determinant of A, B, C, D equals AD minus BC. Right. Parallelograms. Parallelograms. Get the L's working. All right, good. Okay, so it's going to be 1 minus lambda. These pieces here, minus lambda, and then the product of the 2 1s minus that, minus 1. Simple thing, so we've got lambda squared, and then there's a minus lambda, minus 1. So a really simple little quadratic equation, right? This whole thing has to equal 0. Which again, just saying in words, this means that there's no inverse to this thing, A minus lambda has no inverse. That means there is a solution. There is a solution to the original equation, which was AV equals lambda V. We'll constantly kind of say that again, to how that, go through that process again. All right, so we're going to set this equal to 0. Lambda squared, let's do it like this, minus lambda, minus 1 equals 0. So you could use the quadratic formula, that horrible thing, why not? And we get, I'll write it like, let me write it like this. So, well, lambda equals, I guess I should write it as, all right, yeah. 1 plus or minus square root of 5 divided by 2. So it's a bit nasty. Now we've got a square root of 5 in there, which seems a little unfair because we started with 1s and that's true. Eigenvalues come out as nasty things a little bit. Okay, but this is actually a beautiful set of eigenvalues. So let's call them lambda 1 is 1 plus root 5 over 2, and lambda 2 equals 1 minus root 5 over 2. So we'll set these. And there's a reason for that. We usually like to order the eigenvalues. This is an important thing. So in terms of magnitude. Right? So this is lambda 1, if you like this, is greater than lambda 2. It's good to order by a magnitude. I keep thinking of community. By magnitude. Okay. That's it. All right. What does he say? Okay, all right. We should have a paintball version. Funding issues. Okay. So it's good order by magnitude, right? The biggest eigenvalue in terms of magnitude is the main character. All right. So this is, anyone recognize this character? It's a golden ratio, which is pretty special. Awesome. Sometimes you write as rho g, that's a little g. This is the golden ratio. So let me just talk about that for a second, because it's fantastic. So, right, so it appears in lots of ways, but this is sort of the basic story. So if we take a rectangle and we cut off a square, so I'm going to make these x, it's going to be of length x and width 1. And so this length of this one will be x minus 1. So the golden ratio, x equals the golden ratio when the small rectangle is similar to the big one. Right, and this is kind of crazy business that this is supposed to be the most beautiful rectangle, etc., etc. It just actually has a nice mathematical property. This one is similar to the main rectangle. And people got pretty obsessed with this. Lots of paintings have this shape, etc., etc. All right, but it does appear in nature, and this is, as I said, pine cones and pineapples. Got a pineapple there under the sea, and it's got a Fibonacci built into it. All right. Okay. So if it's similar, then the ratio, right, the x divided by 1 has to equal 1 divided by x minus 1. Right? So we take this one out, turn it around, and it's got 1 on this side and x minus 1 on this side. So x over 1 equals 1 over x minus 1. So we're going to require that, so we mess around with this. We get x times x minus 1 equals 1. Put this up here. X squared minus x. I'm going to pull this one over here. Minus 1 equals 0. So it's the same equation. Same as e-value equation. And the solution is 1. I mean, you figure you need the x that's larger than 1. So it's 1 plus root 5 over 2. Right? So that's the golden ratio. There's many things about the golden ratio, but one of the best things is 1 over root 5 divided by 2 is the most irrational number, which is kind of spectacular. And there's a very deep number theoretic reason, because you can write it like this. So I did my master's thesis on continued fractions for some reason, and in a bonanza of work, and continued fractions are very useful things, right? So the idea is that in general you can write any number as blob plus 1 over blob plus 1 over blob plus 1 over blob, and the blobs are all integers, 1, 2, 3, 4, 5. And there's a result in there, and this is where actually the leap day structure comes from, right? The approximation to 365.25, I'm not kidding, this is like, all the crazy sort of Catholic hierarchy, and the scientists got together and figured out from a continued fraction what the best way to approximate the year to the cycle of the Earth around the sun, right? So it doesn't work out if you just have a leap day every year. Eventually things drift, and Easter started to get further and further away from where it should be in spring, and there was a crisis. And the rule now is you have an exception to an exception to an exception. So year 2000 was a leap year, but that's because it was divisible by 400. When it's divisible by 100 normally, it's not a leap year. And then, so 1900 and 2100 are not leap years. So 2000 was this exceptional year that no one noticed at all, because it was just divisible by 4. It was actually divisible by 400. And the English, of course, being English, decided not to do this. And so there's about 150 years where you could go from France to England, and the date would change by about 11 days. Because they're English. And I think the Russian Orthodox Church, maybe some of you probably know this, still doesn't change, right? They have, their Christmas is 10 days later than everyone else's. So it's good for the sales, actually. But it drifted, and so that's why we have this, no leap second, crazy things like that, but we have this strange structure, and it's because if you approximate 365.25, whatever it is, with a continued fraction, they're the corrections that you get. And that's the thing is, this is the best rational approximation to your number, is a truncation of these things. That's the deeper story here. So because this is ones all the way down, if you had a 30 here, or an excellent 17 or a 73, that would, and you cut it off here, that would be a pretty good approximation because 1 divided by 73, really shrinks. But this is the worst. This is the slowest. Its approximation goes as slowly as you could make it. The golden ratio is the slowest. So rational approximation, it's an irrational number, it's got a root 5. Approx is slowest. All right, I know, that's bonus information for you, but there you go. 1 plus root 5 over 2. Really weird. It's really weird. It's easy to create this, by the way, because you have x squared equals x plus 1. So x equals 1 plus 1 over x, and that's it. Right? You just recursively stick it in there. Now you have 1 plus 1 over 1 plus 1 over x. Keep going. You can do this with root 2 and all sorts of root 5. You can play around with them and get their approximations. Fantastic. All right, okay. Okay, so I'm not going to find the eigenvectors. You're going to do that in the first question of Qbert. But I'll tell you what happens at the end. All right, insert question 1 from level 9, if I've got that right, Qbert. Codename Qbert. So you do all this work, and you'll end up with a formula, Fn equals 1 over lambda 1 minus lambda 2, and it's kind of nasty because you've got all those root 5s everywhere. Lambda 1, n plus 1, minus lambda 2, n plus 1. The other thing is you can draw, right, so you can keep doing this. And you keep doing it, cutting off these squares, and then you can draw, and I'm going to make a mess of this, but you can draw a loop through here and you get a logarithmic spiral, which is pretty great. If you go to Harvard Square, just a little bit down Mass Ave towards MIT, there's a little, if you find this is ridiculous, but in the middle of there's a little island in there, and you can see it, it's all built in. There's a golden, and it keeps going out and out and out. I don't know why anyone put it there. It's a very MIT thing to do, but anyway, could be a prank, Okay, so, okay, it's an exciting number. Okay. All right, so we're going to put our characters in here, and you'd end up with this, 1 over root 5. And then we have, 1 plus root 5 over 2 to the n plus 1 minus 1 plus root 5 over 2. There are other ways to get this formula. This is a pretty awesome one because eigenvalues is crazy, right? Sorry, that's a 1 minus. So this one, this is less than 1. This number is less than 1. So this gets crunched as n goes up, in fact, very quickly. So this one approaches 0. So eventually, I mean, you have to keep it in because you have to keep it in to get the exact number because there are root 5s here, right? These root 5s always cancel out. Put in n equals 72. Expand these things, and the root 5s will always cancel out. N equals 73, the root 5s cancel out, because we have to get an integer. Yeah. But this is basically going towards 0, and so you see that the n over fn minus 1 approaches, the ratio approaches the golden ratio. So the Fibonacci numbers, the ratio of them, that's how they grow. So it's exponential growth with exactly the factor of the golden ratio. Super groovy. Yeah. All right. Okay. So, yeah, you get to play around with this and pretend you're in a final exam. That was cruel. Okay. All right. I'm very excited about that. Okay, so we are going to, so I have to talk a little bit about change of basis, just tell you about that in general as a thing. And you'll see that this is part of diagonalization. And then we will get to the crazy thing that happens when we have symmetric matrices to start with. All right. Fear of information loss. Okay. All right. Okay, so this is an example. Diagonalization example, how we do it. Okay. Change of basis. Right, and let me say it here, I guess. This is all from A equals S lambda, A to the power of n equals S lambda to the power of n, S minus 1. Right, you have to construct these eigenvector matrices, find its inverse, raise lambda to the power of n, which is easy. It's a diagonal matrix. Okay. Okay, so we're going to talk about change of basis. It's sort of inserted here, right? This is a more general thing than diagonalization, but I just want to talk about it as well. Okay, so let's say we have this. Give you some examples. x1, x2, and we have our normal thing here. We have I hat. Am I going to do it like that? Maybe a bit bigger. Yeah. This is going to be I hat and j hat, our normal basis vectors. And we're going to put a couple points out here. Let's see, 2, 0. Okay, call this one W1. No, W3, W1. This is 2, 0. Call this vector W3. I'll put one at 2, 2. And put one at 1, 3. Is that right? Yeah. Okay, it's up here. Okay, so we're going to have these vectors. So this is W1. Why did I do this? Okay, I like this. W3, W1, W2 equals 1, 3. All right. So the idea is express. So this is our idea. We're going to express W1, W2, and W3 in terms of a new basis. And let me put it over here. It's going to be something we've sort of worked with already. Okay. Yep. This one, V1, is going to be our new basis. It's all relative to the underlying basis, so that's always a little tricky, but I'll call it 1, 1. We could divide it by root 2, but that would make a bit more of a mess. So let's just do this. And then V2 minus 1, 1. Okay. All right, so here's a bit of a tricky thing. So W1 equals 2, 2. Right, it's 2 times 1, 0 plus 2 times 0, 1. This is the way we've structured it, in terms of the natural basis, right? So by default, it's in terms of the natural basis for R2, the one we really like, should we say, basis for R2. Now, what we want is these points are going to be here still. Here's W3. Let's just call it a point. We won't give it a name anymore. And then over here, this will be W2. Oh, I keep getting this wrong. W1. And this will be up here. W3. So you can see the sort of thing we're trying to get to is that we need to get something that says W1 is 2 times V1. That's what's going to happen here. And 0 times V2. You can see that that's going to work. So let's get to that. I guess I can add here, this is 2 times I hat plus 2 times j hat. All right, good. So how do we do this? We want to express these guys in terms of the v's. So the goal is express, this is a classic little problem to have on an assignment or exam, express the W1, W2, W3 in terms of the V1, V2 basis. V2 basis. Right? So how do we do it? We use something we know very well. We solve an AX equals B problem, which I know you feel very happy about. Of course, so naturally, we solve an AX equals B problem. And this can get backwards a little bit on you, so let's see if we can set it up properly. Okay. So the idea is this. W1 equals 2, 2. So as an example, 2, 2 equals some multiple times V1 plus some multiple times V2. Right? And this is what W will be in terms of this new basis. The point is the same. It's the same point in space. We're just using a different coordinate system. It's a very important thing to be able to change coordinate systems. All right, so, and I know it's exciting. V2, so let's get through this part and then get back to diagonalization. Yes. Right, AX equals B problem. It's an AX equals B problem. This is A, and this is X. We know this. We know our new basis. We don't know this. And of course, we know what it was in the old basis. So I'm going to write it in this way. This will be M. We're going to use a matrix M for these transformations. And then we'll call this W, I'll just call it W1 prime. So this is the point W1 in V1 basis, V1, V2 basis. Which should be 2, 0. It should be 2 times V1 plus 0 times V2. Right? If someone says, I want to get to this point 2, 2, you say go across 2 and then up 2, right? Which is really saying take 2 times your first basis vector that I give you, and then 2 of the second basis vector that I give you. If this is the bases that I give you, I'll say just do 2 of the first basis vector and 0 of the other one. So I'll hand you 2, 0. I'll say 2 zeros. Exciting. All right, so if that's true, W1 equals this, then W1 prime, so we can invert it, equals M the minus 1 W1. So we know this, we don't know this. It's an AX equals B problem. Big AX equals B problems we solve with LU decomposition. This is something where we have a basis. It's a nice, healthy thing. We can always do this. This is okay. Okay because the V's form a basis. So there's always an inverse. Think about that. All right. So let's do it for this example. So M equals 1, 1 minus 1, 1. This is V1 and this is V2. So just write it. So someone says change from this coordinate system to this one or back to the natural one. You have to figure out which direction you're going in. It can be a bit confusing because I think the one that you line up here, you think this is the one that will take you to the new basis. This one takes you from the new basis back to the natural basis, right? So if you have, does that make sense? Let me do this example. So the inverse of this one. All right, write down the inverse for that. right? We can use the inverse of A is 1 over AD minus BC, DA minus B minus C. That's a rule that we've derived in a couple of different ways. Okay, so that is, this is the determinant of A, of course. That's another good piece here. 1 times 1 minus 1 times 1 is 2 at the bottom. And then we're going to swap these so it looks the same. And we get minus signs, so 1 minus 1. This popped up the other day when we were working on a particular matrix. Same thing. Okay. So we would have W1 prime is this blob is a half 1, 1 minus 1, 1 times 2, 2. Let's see if this works. It's a half, multiply this through, we get 4 on top and a 0. So it is 2, 0. And that's what we saw intuitively. Right? This is the point W1, the point W1 represented in terms of the V basis. 2 times V1 plus 0 times V1. Does that make sense? Thrilling? No. Right, so this is, it's 2 times V1, 0 times V2. It's the same point, right? We haven't changed it. We've just said it's a different reference. Okay. And then, of course, to change back, we just use W1 equals M times W1 prime. And so that was just 1 minus 1, 1, 1 times this 2, 0. And if we do that, we get 2, 2. So we're back to where we started from. Right, so this is very important. The point W1 doesn't change, just our representation of it. But our representation does. And that is it for change of basis. Okay, good. So when we go back to, so again, and I said this the other day, and I was sort of mentioned it, so back to diagonalization, back to this, A equals S to the minus 1. Let's think about A times X. This. What's in here? This is the eigenvector basis. V1, V2, Vn. Right, so this is exactly this structure that we built here. We're just stacking the eigenvectors next to each other. It's exactly the same idea. It's a change of basis. So this is a change of basis matrix. And it's going from the V's to the natural basis. And this one is natural to V's. And so you take X, you change it into this new basis. This does all the work. This does the work of A. And it's very simple because it's a diagonal matrix. It says take the first eigenvector multiplied by lambda 1, takes the second eigenvector multiplied by lambda 2, take the third one multiplied by lambda 3, right? Lambda 1, lambda 2, all zeros, lambda n here. And A really, that's what A is. As long as you look at it in the right basis. But because we need to always come back, we need a common point of reference, right? We change for each A. Each A will build one of these, but we always come back to the natural basis. So there's a problem for you to work through on this one. Every time you do a diagonalization, you can think about this as well. But there'll be an explicit problem like this as well. All right. Frowny faces. If you had to describe this with an emoji, what would it be? Okay, all right. Don't tell, it'll hurt. Okay. But there it is, okay. Okay. Great. Let's do some strange things with diagonalization. Okay. Cool. Aha. Okay. Just a note, diagonalization. Actually, did I note that somewhere? So a couple of notes about diagonalization. You have to think about this a little bit. It's a funny business. So some observations, and then the monks will help. Okay, ooh, good. Observations. So a matrix A is, so here's the first one, A is diagonalizable only if it has n linearly independent eigenvectors. Otherwise you can't make S, linearly independent eigenvectors. There's a way of coping in this case, but we're not really going to go into it. Jordan normal form. Okay, sorry. N linearly independent eigenvectors. Otherwise, we can't make S. Otherwise, we can't make S. Right? We need n linearly independent eigenvectors. We've got to invert it. There's just no good. We can't do it otherwise. You always get n eigenvalues. You always get n eigenvalues. You don't always get a full set of eigenvectors. So this has to be true. So bad matrices are missing some eigenvectors. And it only happens, and we had a note about this, so, and it's on one of the online things, so it's only in case of repeated eigenvalues. So that's important. If all the eigenvalues are different, then this is not a problem. It's possible things can go wrong if you have a repeated eigenvalue. So we'll have some more examples about this as we go on. So that's a connection. Let me take this. So the other thing, so this is about eigenvectors. The thing about eigenvalues that you mostly, one of the basic things you get out is that if one of them is 0, one or more is 0, there's no inverse. But that's separate from whether it's diagonalizable. These are sort of these two things you might think are related, but then, okay, let's go up here. Okay. So I've said that, so it's only diagonalizable if we have n linearly independent eigenvectors. It can go wrong if we have repeated eigenvalues. Also, one or more lambdas equals 0 implies the determinant of A equals 0. That's because the determinant of A is equal to the product. There's that pi thing again, I equals 1 of lambda I. So which means no inverse. And then, so there's this, and then there's sort of an important observation that A may have no inverse, but be diagonalizable, right? It doesn't stop that. It's just a good thing to know. Yeah. Right, this one's about eigenvectors, the other's really about eigenvalues. I mean, they're all about eigenvalues, but okay. Okay, there are things I just wanted to make sure you have there. And now, well, I'm still not well. Okay, so let's do this. We're going to have some fun with this. So here's a crazy result. There's just some good things to say there. Okay. Crazy, significant, crazy, amazing result. Okay. So, real symmetric matrices. So real means they have real, they don't have imaginary entries in them. Real symmetric matrices. Always have, it's kind of odd, always have n independent eigenvectors. Always. So they're always diagonalizable. Even if E values are repeated. So that problem we had goes away. Yes, good. So there's that. So this is always 1, 2, have real E values. And so we mentioned this a little bit, imaginary eigenvalues, which we sort of touch on. That's to do with rotation. Right? So these things don't have, so imaginary ones encode rotation. Right? That your matrix will rotate a vector if it multiplies it. So we've got that. Yeah, and then this is pretty nuts. So we have the independent eigenvectors, and actually even more, this is 3, the E vectors of A form an orthogonal basis. Basis for Rn. That seems like too much. They're actually all at right angles to each other. Bananas. What have I done? Querulous looks from the team. The eigenvectors of A form an orthogonal basis. You make an orthonormal, right? Divide by the lengths, but orthogonal basis for Rn. This is ridiculous. Can you see that? Is that hiding behind the?
Yeah. Just the R.
There's an R to the N here. Let me. Put that. It's true. That's a problem. Okay. That's pretty nuts. All right. So we have to try to prove this to ourselves. So every symmetric matrix is really a. If you think about how it works as a multiplicative thing. Its eigenvectors are all at right angles to each other, which makes them incredibly easy to deal with. And there are no rotation things, so all the eigenvalues are real, which means that they stretch these directions, right? They're real numbers. They could flip. They could be minus numbers, negatives as well. But that's all these matrices can do. Okay. All right. Says it's mind-blowing. Okay. All right, and all of this will come back to AX equals B later on. But let's just figure this out. So I'm actually going to prove that they're real. Let's do that. So proof of 2. So one is encased in 3, of course, but this is just sort of a warm up, and then wow, nuts. Proof of 2. Okay, so. Real symmetric matrix. So symmetric A equals A transpose. Aij is real. Or all Aij, all the entries are real. Okay. This is a messy little business, but we'll do it. So proof of 2. So you may not know about complex numbers. All right, that's true. But we'll do it. We'll do it. So let's say we have Z equals A plus BI. And this is the square root of minus 1. Insane. Okay? Complex numbers? A little bit. Electrical engineers like these things. Okay. They call it a J. Okay, so this is going to be A, so it's a real number times this. And there's an important thing called the complex conjugate, which is this. This is called the complex conjugate. Which means take the imaginary part and flip its sign. So if a number is real, so if Z is real, then kind of a funny thing to say is that Z equals Z equals its complex conjugate, which is a way of saying there's no imaginary part. No imaginary part. All right, so the monks arrive and suggest we do this. They say, so monks suggest this. Let's think about A. Of course, it's all about eigenvectors and eigenvalues, so we think about AV equals lambda V. All right, we have this. That's our basic statement here. We have that this is A equals A transpose, and they're real. What we're trying to show here is that eigenvalues are real. They're real numbers. They can't be things. Okay, so we've got to use this. Somehow we're going to have to use the transpose. And we're going to play around with these complex conjugates. Okay, so adjacent to this, we'll write down, we'll take the complex conjugate of the whole thing. And I know this is kind of bananas, but take complex conjugate. And so if we do this to both of these, it turns out you can do that to the product. AV equals lambda times V. So let's put it's just a little bar we put on top. Lots of bars. You know, a thing I'm leaving out is, let me just say it here maybe, that's this. There's this. Also, just a little note here, Z1, Z2, if you take the complex conjugate of those, it's the same as taking the complex conjugate and multiplying them together. Don't worry about it too much. I'm just going to write down. We're going to get it. Okay, so this is real. So that's where we use that piece of information. There are no imaginary numbers in this guy. So this is real. So we're going to use these pieces of information. So it's just A. And then we've still got V with a little character here. And lambda times V. And now we better use the transpose somewhere. So let's just take the transpose of both sides. It's kind of great. And so we'll have V with a hat on it, like this, transpose. A transpose equals V. This is just a number, so it's just a number. So it's lambda, and this will be V transpose like this. Again with the hat thing, and that one's gone away. Right, so we've used the flipping for the transpose rule. So what we're going to do, it is symmetric, so that's where this comes in. Symmetry. We're going to make this is going to be V, A equals lambda, V transpose, like this. There's a bar on that one, a bar on that one, and a bar on that one. The monks are really leading us along a funny path here. Okay, I can't. Many monks died to get to this. All right, as usual. They're not good at living, monks. But these things now look a bit the same, and if I'm sorry, there's a transpose. We can take this equation, pre-multiply it by this blob, and take this equation and multiply it by V on the right-hand side. Okay, so I'll continue here. So make equations match. We'll attempt to do that. Right, so we went across here. And now we're going to go down all the way down to here. We're going to drop off here. So on the left, I'm going to take V. Wow, nuts. AV equals lambda is at the front, there's a V transpose V. So there's a blob here, there's a blob here, and there's a blob here. And so this is the left-hand side, and on the right-hand side we're going to have, so this is pre-multiply by, I'm already done with this, by V transpose with the complex conjugate. And then over here we're going to post-multiply by V. I know people, I know. It's madness, it's a madness. There's this. Lambda bar, V, transpose V, da, 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 da. There's going to be a hat on this one, hat on this one. There's already a hat on this one. So what we're doing here is post-multiplying by V. By V. Okay, so after all that monk-driven madness, this one didn't have its bar, of course. That was the whole point. There's no bar on this one. Everything looks the same except these two pieces. So let's put them in different colors. Oh, that was bad. Yeah. So it was a two-year thing, and I did it in 8 months, and I just went berserk, and then handed it in and came to this place, to MIT the next year. No, I handed it on the Friday, it came on the Monday, yeah. It was really not a good idea. It was fun, a lot of LaTeX. Yeah. Okay, so the only thing that's different between these, everything has to match, so lambda bar has to equal lambda. It's the big story here. So therefore, lambda equals lambda bar, which means lambda is real. You wipe the sweat off. True, we just did that for n by n. Okay, so the upshot is, I've given you a proof because I need to tell you the truth. But this is something you need to know as soon as you see symmetric matrix, real symmetric matrix, you know the eigenvalues will be real, which simplifies that matrix a lot. It doesn't have rotation. Rotation is messy. Okay, so this other one is pretty bananas. That seems very strange that you get orthogonal eigenvectors. So let's do it. It's not going to be as horrible as this because lots of bars. Let's do it for the case where the eigenvalues are distinct. Proof of 2, just to start with. 3, I should say. 3 for case when eigenvalues are distinct. Are distinct, right? So none of them equal each other. So a way to write that is lambda I does not equal lambda j if I is not equal to j. Okay, that's the plan. This is pretty great. So again, the monks say, well, let's think about 2 examples. So we have, let's say, A times Vi equals lambda I Vi, and A times Vj, that thing, equals lambda j Vj. All right, so we just take 2 of them. I not equal to j. All right, so let's take 2 of them and mess around with them. We're trying to show, so the goal is show, what do we need to do to show that Vi is orthogonal to Vj? What's the mathematical statement? Dot product is 0. Right. We want to show that Vi, and our way of doing it is Vi transpose Vj equals 0. We have these equations. We know A equals A transpose. We know A equals real, although that's not important here. Okay, so let's, of course, do some sneaky things. Always with the sneaky things. Okay, more sneakiness. More monk sneakiness. Okay, so we're going to construct a little thing and then mess with it. So it's going to be V, I'll make it I transpose A, Vj. Right, so this looks like one of these things. It's actually just a number. Right, a 1 by n, an n by n, and an n by 1. The whole thing is a 1 by 1. It's a common kind of linear algebra construction. Now, you can see you can maybe see that we can start playing around with the A transpose part in here, and also that A times Vj is lambda times Vj. So the A is going to disappear, and which means we'll get to this product, but we'll get to it in two different ways. So, usual business, we're going two different ways, so we'll go this way, and write it as Vi transpose, and think about that part first, Vj. And then in this direction, all right, so we're going two different ways. This one will group these two together. So if they're grouped together, then we can write it as what's a nice way of repackaging that one? Yeah, so we can use a transpose here, so it'll be A transpose, Vi, Vi by itself, transpose, Vj. Very sneaky monks. Right? So you see this undoes itself to give you Vi transpose, and then A transpose is A. So we've constructed this, so this happens a lot in quantum mechanics, all sorts of things, where you can sort of shift. A looks like it's operating on this one. A is multiplying this one, but we can kind of twist it around and make A operate on the left-hand side, but it's A transpose that does that. All right, A transpose is A, right? So let's do that. Vi, and then still a transpose, Vj, and then we can use the fundamental thing that we have here, which is an eigenvalue equation. So this is just lambda I times Vi, Vj, and there's a transpose here still, Vj. And so all of this is equal to lambda I, Vi, Vj transpose. The transpose is here. So that's the dot product we wanted. Right? That's the dot product we wanted. We can get to it as well over here. So this is going to be Vi transpose. Use the eigenvalue equation here, so it's lambda j times Vj. We can pull the lambda j out, and then we end up with that same product. Vi, there it is. These things are the same, but we said that lambda I and lambda j are different. Okay, let's look at what happened. So we kind of work with A on the left-hand part here, mess with it all the way down. We end up with this, the inner product we're interested in. The inner product is multiplying lambda I here. We use A moving to the right, and we acting on the Vj, and we end up with that same inner product with lambda j. So these things equal each other. All of this implies lambda I equals lambda j, but this is a contradiction. It's against our assumption. Contradiction. So therefore, the only way this can work is if that blob is 0. The inner product has to be 0. All right, these are different numbers. This thing has to be 0. So Vi, that's a remarkable result. Vi, Vj. I know you're psyched about it, but that's crazy.
Going back in the equation to where it was originally A transpose Vi down a little bit, yeah, down. How is that equal to?
Back to here?
No, the next one.
Oh, yep. Right. So this is using the fact that it's symmetric.
We know that already.
Yeah, so that's a key part. So it's for real symmetric matrices that this is true. No, it's fair enough, yeah. So real symmetric, the entries have to be real, the matrix has to be symmetric. So symmetric matrices have very kind of beautiful properties, and this is one of them. So that's super exciting. We will cope with it. I'll have to do it on Tuesday. We'll cope with the fact what happens when lambda I is repeated, right? When you have some eigenvalues that are repeated. Other questions? Everyone is so happy about it. All right, so it's pretty amazing. That's weird. That's a weird thing. So let's go one step further and write down what this means for diagonalization. Oh, I don't think this is a lie. I think it's true. Okay, diagonalization. Got it. Yes. All right. Okay. So, super exciting. So, so in the case for A equals A transpose, and we're talking about real ones, but for A equals A transpose, we write S, which equals this one, V, right? So it's the eigenvalues, V1, V2, eigenvectors, I should say, eigenvectors, as Q. So we talked about these orthogonal matrices. It's an orthogonal matrix now. So the inverse is beautiful. So the inverse, we had S to the minus 1 before, well, we had to calculate this. So now it's just Q transpose. Becomes Q transpose, right? Because Q is an orthogonal matrix. Right, all the columns of Q are at right angles to the ones that don't match up with them in Q transpose. Okay. So if A equals A transpose, then we end up with this. A equals Q lambda Q transpose, which is quite spectacular. This is much easier, right? This was S. This was S to the minus 1. Beautiful. Very easy, right? Much better than computing a transpose. Yeah, the best matrices have orthogonal eigenvectors. Let's write out one more piece associated with this. Should I do it? Okay, so here's an example. Let's take A equal to 3, and we're not going to compute all the things. 3, 1, 1, 3. You find V1 equals 1 over root 2. It's the same business as before. And V2, we're going to normalize them. You have to normalize them now. Minus 1, 1. And yeah, so we end up with A is equal to 1 over root 2. 1. Yep, minus 1, 1, 1. And in the middle, we end up with 4, 0, 0, 2. So I should write here. Lambda 1 equals 4. Lambda 2 equals 2. If you solve all this, we find this. And this is, and there's a 1 over root 2 here. 1, 1, 1, minus 1, 1. Right, so this is Q, lambda, Q transpose. Okay, so there's one more thing that comes out of this. This is the last bit that I want to tell you today, which is kind of ridiculous. Okay. Even better. it turns out then we can rewrite our matrix completely as a sum of projection operators. Okay, so the spectral theorem. This is bananas. Okay. You can actually write this matrix. Let me write it out. In this example, A equals, it's going to look like this, 4 times 1 over root 2, 1, 1, 1 over root 2, 1, 1, plus 2 times 1 over root 2, minus 1, 1, and then a 1 over root 2, minus 1, 1. And in general, this is for a 2 by 2. It's lambda 1 v hat 1 v hat 1 transpose plus lambda 2 v hat 2 v hat 2 transpose. Okay, this is really strange, right? So I'm going to derive in a second. This is a projection operator. If you look back when we did projection operators, well, projection operator, we had P equals A hat transpose if we're projecting some vector B onto some direction, and here's A hat, right, which is a unit vector. If we're projecting onto it, getting that part of it, let's say it's here, right angles, this vector here is A hat transpose times B. So A now is being, this is only for these symmetric matrices. It's only for symmetric matrices. These things have to be at right angles to each other. Right? So this is still for symmetric matrices. They're so simple, you can write them as a bunch of projection operators. So what does A do when it multiplies X now? It projects it onto the direction of V1, multiplies it by lambda 1. Projects X onto the direction of V2 and multiplies it by lambda 2. I've written down the example, and let's derive it in general. Okay, so A equals Q, lambda Q transpose, this thing. So we've got all these vectors in here. It's V1 hat, V2 hat, Vn hat, and then we're going to have lambda 1, lambda 2, down to lambda n. This is great, this is what we're going to do. And then Q1, no, it's not Q1, V1 hat transpose, V2 hat transpose, Vn hat transpose. All right, so we start multiplying these things out. And we'll leave the first one, V1 hat, V2 hat, V3 hat, Vn hat, leave this. Multiply into here, we'll end up with lambda 1 times V1. And we can only do this because this is Q transpose. Right, if it was the inverse of S, there'd be a big mess. But the rows are very simple. So the rows are simple. Only in this case. So if we multiply through here, we get lambda 1 times that row, lambda 2 times the second row, V2 hat down to lambda n, Vn, and then we've got this block multiplication. We can think of this as sort of a giant dot product. There's this one times this one times this one. So you end up with lambda 1 V1 hat V1 transpose plus lambda 2 V1 V2 hat V2 hat transpose to lambda n Vn transpose. And so in general, it's the sum of, and this is an amazing thing, lambda I Vi hat transpose. That's A. It's very, very weird. So A looks like, I want to add one more little pictorial part here. A, of course, is a big square matrix. These are little outer products. So those outer products we talked about early on, those outer products are everywhere, right? Each one of these is a little outer product. And this is where we'll get to this idea that matrices can be made up of all these little bits of Scottish tartan, which is kind of strange. All right, that's a very fundamental result. It's a very basic, important piece of linear algebra. And you get to play around with it in Qbert. All right. Okay, people, we're moving along. It's good. You do have plenty of time for this final exam. And I'll send out a practice one on Tuesday, I guess. Or before, maybe before. Yes. Bye.